Hi, welcome back to another past paper walkthrough. Today we're doing Mechanics 1 again for section B for the year June 2015. I didn't say that last time. So let's get right on to the sixth question of the paper. So the battery on the car is flat so that it doesn't start, so it have to bump start it by running down a hill. And right, so these are a lot to read. Make sure you read everything, and everything is summarized in a diagram. So the mass of the car is 750, and the two people's mass are 50 and 80 respectively. Part 1, between A and B, they push the car, and Martin is in the car, pushing the car, Carol is inside the car, and the car is accelerating at 0.25 meters per second squared, and show that the resistance is 100 newtons. And for part 2, they stop at B, and Martin tries to push the car up the hill, and the resistance is 100 constant. Find the acceleration of the car when Carol is no longer in the car. And part 3, while between B and C, Carol opens the window of the car and pushes it from outside as shown below, and Carol is able to exert a force of 150 newtons parallel to the surface of the road, but at an angle of 30 degrees. So find the acceleration of the car with Carol's push. Now finally part 4, at C, both of them get into the car, and starting from rest, let it run down the hill using the gravitational acceleration. And if the car reaches 8 meters per second, they can get it to start. So does it reach 8 before it reaches the end of the slope? So Martin is exerting 300 newtons, and therefore F is 300. Subtract by resistance, because it's the resultant force, equals F. And that will equal to MA, where the M is the car plus Carol, which gives you 800 kilograms. Acceleration, which is 0.25, which is also 1/4, and therefore this is 200, equals to 300, subtract by R. By rearranging, R equals to 100 newtons. So that is part 1 done. So right now we need to show that if the car can go up the slope or not when, say, Carol is in the car, and when Carol is out of the car. So Martin is pushing up, so let's draw a free body diagram. It always helps to visualize things. So this is a 1.5 degree slope with a mass on top, which is a car. Martin is pushing 300 newtons parallel to the slope, and there is a force downward called the weight, mg, which goes down vertically. So we do not need to care about the normal reaction force, because it has nothing to do with the line of action or the line of movement, and therefore we just need to care about the mg. And mg, if you do not know, it makes the same angle as the horizontal to the slope as the so basically this angle between the force, the weight, and the normal of the plane or the slope is the same as the angle between the slope and the horizontal. You will know that if you've done enough of the slope questions, and therefore you can use the previous method that I taught you last time to find that the force going down the slope that way is equal to mg sine of 1.5 degrees. So we have that force and we have the upward force. So the car can be pushed up if 300 is greater than mg sine 1.5. So let's see if mg sine 1.5, well, let's see if 300 subtracted by mg sine 1.5 is larger than 0 or not. So let's find a numerical value. M, if Carol is in the car, is 800, so that is 300 subtracted by 800 g sine of 1.5. And if you plug that into the calculator, that gives you 94.7. And given that you have a constant resistance of 100 Newton backwards, you have to take another 100 off. I actually forgot about this factor, so make sure you have all the forces. So also draw a resistance force of 100 newtons, and that, if you subtract 100, gives you a negative value, which means that he cannot push the car up the slope. So I just say cannot. What if Carol is not in the car? That means that this m will be 750 only. So let's do the same equation. 300 take 750 g sine of 1.5 take 100, which gives us 7.59, which is greater than 0, and therefore he can push it up. And find the acceleration when he is pushing it up. So you've got 7.599 as your force, the resultant force, and just divide that by mass, which is 750. Gives us A equals to 0.0101 meter per second squared. For part 3, we have Carol pushing the car at 30 degrees using 150 newtons. So let's find the total forward component. So 300 is non-changed or unchanged. Add 150 cosine of 30. That will give us the force, forward force that is. So 300 plus 150 cos 30 gives us 429.9038 newtons. So we'll use that. Now we're still on the slope, and the slope has 1.5 degrees. So let's draw another free body diagram. 1.5 degrees with a mass, with a weight of, this time Carol is out of the car, so 750 g, and also Martin, both of them are pushing, so that is 429.9038 with a constant resistance 100 newtons, and yeah, those are all the forces. So now Newton's third law, the car is accelerating upwards, and therefore 4 to 9.9 is the larger number, or positive. Subtract by 100, subtract by 750g sine 1.5 will give us MA, which is 750 this time. So let's plug these numbers into the calculator. This gives us 137.5 equals 750 A, and therefore A is 0.183 meter per second squared. Finally, part 4, we're going to find if they can start up the car or not after all those hard work. So there are only two forces to consider, because right now Martin and Carol are both in the car, and therefore the mass is equal to 750 plus 50 plus 80, which is 880 kilograms, and we have a force of mg. The slope is 3 degrees, and therefore the force going downwards is 880 g sine of 3 degrees. That's going down, and we have a constant resistance of 100 newtons, and that will give us MA, which the M is 880. So let's find A, then we can use SUVAT. 880 times 9.8 sine of 3, take 100, gives you 351.345 is 880A, and therefore A is 0.399. 256. That's meter second squared, meter per second squared. And since we have the acceleration, we have the distance, which is displacement rather, 100 meters, and we have the well, we need to find the velocity, and we know it's starting from rest, and therefore u is 0. We can use s equals ut plus half at squared, or actually it's better to use v squared equals u squared plus 2as, because then we do not need to care about the time. So v squared equals 0 squared plus 2 times a times s, which is 100. So v squared is just 2 times 0.399 times 100, gives us 79.85, and v, when you square root it, is 8.9359, which is larger than 8 meter per second. And therefore, yes, the car starts. So that is it for question 6. Question 7 is the last question of this paper. So a box of emergency supplies is dropped to victims of natural disasters by helicopters at S1000 vertically, and the initial velocity is 0. And part 1, find an expression of the velocity in terms of t between 0 and 10, and show that when t is larger than 10, v is 50. Then draw a sketch of the v against t graph. Show the height h above the ground is given as this expression. Then find the height of the box when t is 10. Part 4, find the value of t when the box hits the ground, which means that this expression is 0. Part 5, split into A and B. Some of the supplies are damaged when the box hit the ground, so measures are considered to reduce the speed. So carry out the suitable calculations to see if how much the speed are dropped. So part A is just decrease the initial height. Part B is give it a parachute so that the acceleration looks sort of like this. So since we have acceleration and we need to find velocity, let's integrate by t. So v is the integral of 10 minus t dt. And these are just simple integrations. 10t take t squared divided by 2 equals to, well, v. And at time t equals 0, there's a c as well. At time t equals 0, the whole expression is 0 because velocity is 0, and therefore we know that c is also 0. And therefore v is 10t take a half t squared, or t squared over 2. Now show that when t is larger than 10, v is 50. So let's just put t as 10 in there. So when t is 10, this is 100, take 100, half of 100, which is 50, which gives us 50 meters per second. And this 50 meters per second, when put into this expression, this is our initial condition. And so A is 0, v is integral of 0, which gives us a constant. So v is c, and because the initial velocity for t equals 10, initial s of t equals 10, not t equals 0, is 50 meters per second. C is 50, and therefore the velocity for t larger than 10 is always 50 meters per second. So for part 2, we need to sketch a curve of v against t for t equals 0 and up to t equals 20. So the way that you can do this is to use your previous answer. So when t is 10, we know that it is at 50. So let's say this is 50. And we know that acceleration is 0 for any time after 10. And therefore this is just a horizontal line. It is horizontal despite how I've drawn it. Use a ruler for this part. Then for the path before, use this equation. You will see that the acceleration keeps decreasing, and therefore the gradient of this curve keeps decreasing. So it starts off fast and high, then slowly decreases until it reaches 0 at t equals 10, and it keeps horizontal for the rest of the curve. So that is part 2. So we need to find the horizontal height when between t is 0 and t is 10. So we know that the velocity of the box is this expression, and because it's falling from 1000 meters or 1 kilometers, we know that if we integrate this expression, we get the displacement as from the top to the bottom, but what we really want is the h from the bottom to the top, and therefore we can just get that by doing 1000 subtract by s, where s is the integral of 10t minus half t squared. So let's first find s. Integrate this expression 10t plus minus 1 over 2t squared dt is just 10t squared divided by 2, take 1 over 2 divided by 3, which is 1 over 6, plus a constant. And we know that the initial s is 0, and therefore we know that c is also 0 by just putting in 0 in t's. So s is 5t squared, take a sixth of t cubed. And we want to find h, and h is 1000, take s, and s is given in terms of t as the following. So that is 1000 subtracted by 5t squared plus a sixth t cubed. Remember the negative signs, that's a negative negative, gives you a positive. So that is the expression that you've been asked to get. So find h1t is 10, simply put in t equals 10. So 1000 subtracted by 500, add a sixth of 1000, and that doesn't divide nicely, you'll get a recurring number. Gives you 2000 over 3, an equivalent of 666.6666 meters, or 3SF 667 meters. So part 4, we need to find the time at which it hits the ground. And we know that the first 10 seconds, the box have dropped 666.6 recurring meters worth of fall from the previous question. Well, actually, this is the height at which the box is at time t. T equals 10. So let's visualize it. This is a total of 1000 meters, and the box is right here at this moment at 666.6 meters up from the ground. And we know from even earlier questions that this bit only travel at a constant velocity of 15 meters per second, and therefore we can calculate the time, the remaining time. So in the first section, the top bit, we used 10 seconds, and we just need to add the second bit. The second bit is just the remaining distance, 666, that's 6.66, 0.6 recurring, divided by the velocity, which gives you a time, and this is a constant velocity, so it works, which will give us 13.3 seconds, and therefore the total time taken to drop from the top to the ground is just 23.3 seconds. So for part A and B of part 5, we need to see which model is an improvement, or is there any change to the condition at which the box land, because apparently it's too fast. So let's have a look at A, the model. The height is dropped from 1000 meters to 500 meters. And from previous calculations, we know that time taken to reach terminal velocity is 10 seconds. Because it's technically the same model, it's just the height that changed. And the distance covered in that 10 seconds is 333.3 meters. And if you drop that height by 500 meters, you still got 500 meters to drop, and therefore you still have enough distance to reach terminal velocity. And therefore the conclusion is same terminal velocity. And therefore it is of no improvement. What about B? The model is modified so that it reaches terminal velocity at t equals 5, and the acceleration decreases much faster now. So let's see how what is the terminal velocity. So do practically the same thing. So 10t subtract by t squared, because it's 2t squared divided by 2, and that is equal plus c as well equals to phi, and phi initial is 0, so c is also 0, and therefore phi is 10t take t squared. And we know that terminal velocity is 5 meters per second, well 5 seconds, sorry. So plug in the 5 into the terminal velocity, so you get 50 take 25, which gives you a nice terminal velocity of 25 meters per second, which is half of the previous terminal velocity, and therefore it's an improvement. So that's it for this question and the paper. So for this section, it's really not too bad. It's sort of tricky in the fact that you have a lot of very similar things to calculate for the first question 6, and also for question 7. It can be very difficult to do if you do not know what you're trying to do, and knowing that acceleration is d phi by dt, and knowing that velocity is d x by dt is also very important. And so that concludes for this entire MEI Mechanics 1 paper. I hope you have learned something, and I will see you on my next one.